Thank you. Well, good morning. Welcome to early morning sessions. I'm glad all of you are here. Hope you had loads of coffee. I'll make sure that I keep you awake. These are some of the URLs. You actually might want to keep it open on your tab. I had put instructions in the schedule to have your laptop set up if you really wanted to follow along. I would recommend not to do it now because you're going to be spending some time, and given that we have a big group over here, everybody downloading and installing on the laptop could be a diversion. So I really want to concentrate on the workshop today. I'm going to walk through the introduction, and I'll walk through the notebooks myself. And since this is something that you can actually take home with you, if you need sleeping aids tonight, you can probably use that as a tutorial, so it'll actually help you. So let's get started. Again, welcome. This is going to be a session about introduction to array for distributed computing and machine learning using Python. Basically, we had PyData. Actually makes sense to do that. And I just want to get to know what your background is and where you're from, so I can sort of understand and calibrate the presentation. So how many of you actually have heard about Ray? Good. You guys can go home then. How many of you are using Ray? Good, then you can stay. How many of you consider yourself data scientist? How many of you consider yourself machine learning? How many of you consider jumping on the bandwagon to be model foundational builders? Okay. And I'm going to ask you a tongue-in-cheek question. How many of you are Python experts here? It's like going to a Catholic church and asking, is a Pope a Catholic, you know? Well, welcome. Thank you very much. My name is Jules Damji. I am a lead developer advocate at Scale, part of the Ray team, very much embedded in the Ray engineering team. And prior to that, I was a senior developer at Databricks, where I spent about 6 years contributing to Apache Spark and MLflow. And then prior to that, I was at Hortonworks doing very much the same thing. And then prior to that, I held many software engineering positions at some of the notable companies. So I was very fortunate. I was very, very, very pleased to be at the right time, at the right moment, to really see the evolution of this fourth evolution we're actually having called foundational models. So I think this is actually great to be part of it. Just been very fortunate to be part of this particular journey. Who do I work for? I work for a company called Scale, and we were the original creators of Ray. And Ray sort of emerged from Berkeley's Rice Lab, which was a successor to the AMP Lab, and where Spark was born, Tachyon was born, Mesos was born, Café was born. So these were sort of what I would call the Berkeley's innovation labs, where they were very tied much with industry, and these were the open source projects that were born. And what do we do? You know, what is our mission? Well, we provide you the unified platform to deploy and manage your scalable Python applications. And why do we do that? Our mission really is to make sure that scaling is today a necessity. It's not an exception. And we want to make sure that anybody in this particular room who's a Python programmer can actually take advantage of that. It used to be the case in the early days where you actually had to be a distributed machine learning or distributed software developer to know the internals of that. We wanted to sort of abstract it away and make that a possibility for everyone, because scaling is a necessity and scaling is difficult. So here's the agenda, what I'm going to cover today. Give you sort of an intuition of why and what Ray is and Ray's ecosystem. And then we'll drop down into Ray architecture and components, and what are some of the individual Ray core design scaling patterns that actually make this actually possible. And you can't be at a conference today and not talk about foundational models and not talk about generative AI. And I just wanted to sort of touch on just a little diversion about how Ray fits into the generative AI. And we just consider large language model as just one of the workloads that you can actually use to Ray. And one of the interesting bit about that, the companies who build these foundational models such as Cohere and OpenAI, they use Ray initially to train and tune these models. And then we'll go in a class for modules 1. The rest of them I'm going to have you do extracurricular activity because we don't have the time. This is normally like a full day course. Okay, so why Ray? I think they are, when the original researchers were working on this particular project at Rice Lab, they were quite prescient about sort of thinking about 3 industry trends that were sort of dominating at that particular time. We're talking about 2016 to 17, and this was prior to Spark, which was about 10 years earlier. And they realized that machine learning is pervasive, is going to be pervasive, and it's true. Today, ML is everywhere, right? It's on your laptop, it's in the industry, it's in robotics, it's in health science, all over the place. It's a pervasive thing. And larger compute infrastructure is actually needed to build large language models, or models today are getting larger, so you need a lot of compute power. And that necessitates that if you're going to be doing machine learning at a large scale, distributed computing became a necessity. It wasn't an exception. In the older days, you use HPC or you use MPI to write, and you really had to be very expert in able to write this distributed application. Today, it is a necessity, and if something is actually a necessity and it's going to be ubiquitous as machine learning is today, you have to make sure that you can actually use it easily. And I would contend that Python, because you're here today, is the default language, right, for machine learning. If you look at all the frameworks out today, all of them actually have Python bindings. They might be implemented in C++, they might be implemented in C, but they do have Python bindings as a first-class citizen, and that is the default language. So those were the 3 primary sort of pillars, the foundational ideas that actually drove into the evolution of Ray at that time. Now, we are blessed with what I would call the blessings of scale. Now, if you look at the chart, on the far left-hand side and how actually the models have evolved, today your laptop can do anywhere from 10 billion to maybe 100 million instructions per second, floating point instructions per second. But when you come to building large models, a lot of machine learning models, both traditional statistical models and today's foundation models, we are talking about exponential way in which you actually need that. But these blessings of scale kind of also introduce another problem which we call supply and demand. Now, we know that Moore's law is dead. Rest in peace, he passed away last week. And we can see that the GPU somehow was meeting some of that particular demands. And the hardware accelerators like the TPU kind of met that particular demand. But if you look at the linear scale in which the compute power is actually needed, it's about 35x every month. And there's a huge gap, right? There's a huge gap between what today's accelerators can provide you and what the demands of this particular models are. And we contend that the only way you can actually do that if you actually go distributed, right? You only have to distribute, otherwise you just can't do it. You have to go across the entire cluster. And the third one was the PyData ecosystem, right? You can actually see, some of you actually have worked with this particular libraries, you're working with these libraries. And these are the sort of the traditional libraries that you actually use to do your number crunching or your data transformations. And the libraries on the right-hand side all have Python bindings that allow you to do machine learning, both statistical and deep learning as well. So that was sort of the third trend that people actually saw going. So I've talked about why Ray, right? What was the foundation? What was the philosophical reason of doing that? And we actually begin to see the massive adoption of Ray today for doing machine learning at scale. So I'm going to now switch about what is Ray, right? What is Ray? I'm talking about why Ray and what is Ray. And I think one thing I want you to take away from this presentation, if not anything else, is a simple general purpose library for doing distributed computing. And it comes out of the box with 3 kinds of abstractions that we're going to talk about today. They're going to have workshops on. And the library is actually built on top of that for you to be able to scale your machine learning workloads. Now, when I talk about machine learning workloads, what am I talking about? I'm talking about data ingestion, data transformation. I'm talking about doing batches and distributing your data across workers in a cluster where they can actually do training. So there's a library for that. We're talking about batch inference or hyperparameter tuning is another big library tune that comes out of the box, but it's actually built on the Ray core primitives. We're talking about reinforcement learning, which is an important part today in both building foundation models, but also in the gaming industry and in other areas where you're actually solving an optimizing problem and you're learning as you actually go along. And the good thing is it actually runs on your laptop. As you saw today, you're going to be running on your laptop. It runs on any of the public cloud they actually have. It's open source. You can run on-premise and you can run on Kubernetes. But another way to look at it is layered cake of functionality. And what I mean by layered cake of functionality, right? At the bottom, you actually have all the clouds that you can actually run on. And then one level above is the Ray core. And we're going to talk about what Ray core is today. And Ray core sort of provides you these abstractions to allow you to write your Python application, convert them into either tasks, which are stateless functions, or actors, which are stateful actors. And then the objects is a shared memory that is across the cluster, and we'll get into that. And this is sort of the Ray core on which these libraries are built, right? So if you go one level above, we have this thing called Ray Air, which is a unified toolkit that allows you to build these ML applications. So you can do data training, transformation, you can do train, you can do tune, serve, and RLib. And if you don't care about these things, right, if you're not a machine learning programmer, let's say you're a physicist, or you are a geologist, or you're a climatologist, we have one in the room, who wants to scale the Python applications to do numerical computations, you can use Python tasks to do that. So it sort of serves two purposes. You can actually use Ray to build your machine learning libraries using the existing libraries, and they work very cohesively, or you can just use Ray to do other distributed tasks. And just to give you this architecture diagram, the Ray Air I'm talking about has got all these different integrations that we actually have that allows you to do end-to-end. So for Ray data, you can use any of these libraries that actually are integrated with Ray. For training, we have integrations with PyTorch, XGBoost, any of the popular libraries that you actually are using today to build both your statistical or traditional model, or also using deep learning models as well. And if you're doing hyperparameter tuning, we have a tuning library, but you can actually provide your schedulers, you can provide your search algorithms, you can provide any of the third-party algorithms that are provided by this library that you can actually work with tune. So if you're doing a massive hyperparameter tuning, and let's say you want to use Asha scheduler, and you want to use early stopping, and you want to provide a search grid on which you can do that, you can do that with RayTune. This is sort of the advanced one. And if you're doing experiment and tracking, which is an important part, if you're building machine learning models today, you need to track exactly what parameters you use, all the artifacts you actually created. And so we have integrations with that. We don't provide that as part of the Ray, but we provide integrations so you can actually do that. And so on and so forth down the line. And these are sort of very scalable because they're run on top of Ray, so you can actually scale them across. So that sort of is the whole idea behind it, the very high level, what Ray is all about. Now I'm going to go down a little deeper into what the Ray architecture is, because I think it's important for you to understand behind the scenes how things are actually laid out, right? Now, if you look at this architecture, it's no different from any other distributed computing that you have, such as Dask or such as Apache Spark. The idea is that you're going to have workers, and the workers will be executing some job on the top of that. But there's something quite unique about this particular anatomy, is that the head node actually has the driver and the worker. And the worker can be any Python process that's bound to a CPU. So if you have 8 CPUs, you can have 8 Python workers working. There is a Raylat, which actually has 2 threads. One is a scheduler, and the other one is an object store. And scheduler is responsible for managing and scheduling tasks and actors and making sure that your tasks are scheduled to a particular node where you actually have enough resources. And the object store is a shared memory object store, which is built on top of Apache Plasma. And the object store allows you to store any objects that you actually want, which are greater than 100 kilobytes. So you can share this object store across. So you actually have a shared memory store that goes across. And then when objects are created, they're actually put in the object store. And if you have processes running on the same worker, or any workers running on the same particular work node, they can get the object store 0 copies. So you're not copying it. There's no IPC going on between processes. They just use the shared memory. And that's something quite unique about that none of the other distributed systems have that. You have a distributed scheduler. You don't have a main scheduler. Any of the Raylets can actually schedule your test. So you have a distributed schedule. You have a distributed object store where you can actually share any objects that you actually put in. And then there's a global store that has, think of it, it's a meta information about what processes are running where, what tasks are running where, what are the resources, what are the GPU resources. Anytime when Raylet wants to schedule something, it consults the object store, and periodically, every 10 milliseconds, the object store broadcasts the current state of all the resources, how many hardware resources I have, how many GPUs I have. And if a new worker comes in, it registers itself with the global object store, and then actually it broadcasts. So the Raylet at any point has an idea of what is my resource across the entire cluster. And this all happens behind the scene. You don't have to worry about it. Ray sort of takes care of that. So that's the anatomy of a cluster. And now I sort of want to get into some of the design patterns that Ray supports. And you probably have seen those design patterns in other programming language and what's so unique about that with Ray and how it actually projects or translates that into APIs. So some of you probably have heard about this design patterns. Have anybody read this particular book? Right? So design patterns were introduced in our consciousness by this gang of four, right? And they sort of introduced this high-level concept of how design patterns are used in high programming languages. And in Ray, you actually have three design patterns that we share and we implement. One is the parallel Ray tasks. And Ray tasks are nothing but any Python function that you have, you can convert that into a distributed setting. And that allows you to run allows you to run tasks across the cluster, and that can actually scale. And these are stateless, right? Which means that there's no state maintained. The second thing I talked about is the Ray object as futures. And futures are something that you probably have come across. If you're using Scala, or if you're using today's Python, futures are something that materialize later on down the time of your machine, of your application, and they can be fetched when they actually materialize. And those are normally blocking calls. And this ability to do asynchronously allows you to parallelize stuff. So the combination of parallel Ray tasks and the ability for the tasks or actors to create these features as objects that they might return. They are stored in the object store, so we can just schedule something. It will go and do the tasks. When the tasks are ready, you can actually go and fetch them. And then Ray actors just extend parallel tasks. So if you have a particular Python class that you have and you want to make that into a stateful service or a microservice, you can use Ray actors. And that allows you to do message passing between actors or between tasks and actors. And these three are the fundamental abstractions that are the core on which all the other libraries are actually built. And these are sort of the solid core. You don't have to worry about scheduling, you don't have to worry about memory management, all that's actually taken care of by Ray itself. You just write your functions or write your Python code using these abstractions. And we'll see some of that in the workshop. And there's some links over here. By the way, the slides are in the GitHub. There is a slide directory. If you go to the directory, there is a PyData Seattle directory. You can always get to the slides if you want to follow along. Now, some of the scaling design patterns which are very common that you actually have either worked with or you have encountered are what we call scaling design pattern. One is what we call different data, same function, right? Now, this is very common for your machine learning workflows such as batch training and inference. What you're doing is you're actually taking a large data set that you actually have and you're creating into shards, and you're using the same function or the same model or a copy of a model which is across the cluster, and you're predicting it, or you're doing inferencing, or your batch inference. Different data, same function, right? A variation of that is you're using the same data, but you're using different function. So let's say you actually want to train 2 or 3 models. You want to do a linear regression, you want to do XGBoost, and you want to do decision tree on the same data, but you want to use different hyperparameters to make sure that you can train those different models. So over here, you're using the same data, you're training 3 different algorithms or 3 different functions, and you're getting the end result at the back, and you're picking the best one. And the batch training is no different, right? Batch training is that you actually want to use different data, but the same sort of function. So when you do distributed training, you want to take the data, you want to shard it, and you want to give it to the same model, to the same function, or your objective function to do the training. So this is sort of at a high level what it is, and we'll go through some of the exercises that are in the workshop. So those are sort of the design scaling patterns I talked about. Now, how does that translate into the APIs I talked about, the 3 design patterns I talked about? How do they translate into Python code? So here I have a Python function, just some random function. I have a class, and then I have some NumPy assignments that I want to now convert that into its Ray equivalent. And all I need is I just put the decorator called radar remote. And then what radar remote does, or at least what the driver does, or wherever this thing is doing, the raylet will actually schedule this particular task on any one of the nodes that you actually have. All right? Simple as that. You don't have to worry about the IP address. You don't have to worry about where the ray cluster is. You don't have to worry about where the worker node is. You can just do that by doing radar remote. The second bit is I talk about stateful functions, is where you actually take a class that you actually have and you want to maintain a particular state, and you just do the same thing. You decorate that with data remote, and that converts that into a distributed service or a distributed object store running on each and every node. Now, each and every instance of a ray actor you create will have a different instance running. Right? One instance will be scheduled on one node. If you create another instance, they'll be scheduled on the third node, and so on and so forth. And then finally, if you have data that you actually want to store in distributed object stores that other workers in the cluster can get access to it, all you do is you use these very simple APIs, ray put and ray get, and then these will be somehow stored into a particular ray object node with that particular data on it, and then any worker running on that particular node can actually use row.get. If the object A, if object A is created on node A, but there's a process running on node B that requires node A, then the primary copy is copied over. And then once that, you actually pretty much will have it across. So there's an initial overhead of copying it over. But once you actually have that, you'll have shared data across. So those are sort of the Ray APIs I talked about. Any questions? Yes?
For the actor objects, is that, sorry, is the actor the class, or is the actor every instance of the class?
The actor is an instance of the class, right? So when you actually create an actor, you're saying, this is my template, right? So you'll see how we actually create an instance. So when I'm doing the class.remote, see this call over here? Class.remote, I'm creating an instance of that. And then when I want to invoke any of its methods that I have, which is this method, I just invoke the method name, and then I pass the arguments, right? If I have any constructor arguments that I want, I just provide that in this particular call, and it will go ahead and initiate that with the constructor. So that's a simple example, but we'll see that in the workshop.
One more question.
Yeah.
In the earlier slide, you said that the objects are kept on a shared memory.
Mm-hmm.
So isn't it happening over here, like distributing multiple objects?
Yeah, so good question. How does this actually get shared in the memory? Let's say this particular object gets placed on node A, right? And there's a task that's running on node A. It'll be able to use that object right away. There's another task B running on node A. You'll be able to get that through zero copy because processes share shared memory, so you don't have to copy into processing. Now, let's say there's a class C or task C, which is running on node B, and it needs a reference to A. Somehow, you need that particular doc. You actually send it a reference, and this task will say, well, where is this particular node? I'm going to find out from GCS where is this particular node. And then it will ask the raylet to go and copy it. So this particular slide that I had, the raylet knows exactly where the reference is. It's going to copy it over. And now this is a secondary copy that I have. Right? And once that is out of scope, this will go over. The primary copy will remain. And so we have a distributed reference counting. And when all the references are gone, yes, we are copying. Yeah, we're using gRPC to actually copy data. And once it's over here, then it's stored in the shared memory. So just to give you a sort of an illustration, what actually happens is that when you actually create a particular task, you can provide the resources that you actually want. So here I said, I want to reserve 2 CPUs for this because all I'm doing is A plus B. No pun intended, but I'm just giving an illustration over here that I need 2 CPUs for that particular that. And then what I have is now this is going to be scheduled on any one of the worker nodes that actually has 2 CPUs reserved, and it'll start executing that. So that's how this particular remote function is done. When it does A plus B returns, what happens over here is that it will return right away. asynchronously, and it'll give you an object reference. And then the object reference can actually be fetched to get the result A and B when it materializes, right, asynchronously. So that's the great thing about tasks, is that you can create thousands of tasks, and all of them will be scheduled right away. And then they'll start executing. And when they are finished, they will actually put the objects in the object store. And then you can actually have an ability, in a wait while loop to actually go ahead and fetch those things. In a similar manner, Reactor actually has the ability to specify the same thing. I want 4 number of GPUs, and I want this particular actor to be distributed across hosts that actually have 4 GPUs. So when I request the 4 GPUs, what happens at this point is that the Raylet scheduler say, okay, I don't have 4 resources, so let me broadcast that to GCP to find out which Raylet actually has 4 GPUs, and I'm going to get a list from that. And then when that list, I get that particular list, the Raylet will actually schedule now that particular that particular host actor to be scheduled on that particular host. So all these things are actually happening behind. We really don't have to worry about it, but I just wanted to give you an intuition of what happens under the hood. Okay, let's look at some code, right? Here we actually have a function that I'm taking, which just takes in a file and then returns a NumPy array of that. And then I have a function called add that actually takes 2 references to it, or 2 values or whatever that is, and then computes the addition of those, and then I'm doing a ray.get. So what's happening over here? Well, when ray.remote is scheduled, it's going to read that particular file, and it will convert that into a NumPy. It will return a reference, right? It's not returning actually data, it's just returning a reference. And then add ray dot takes 2 arguments, A and B, and I'm going to add those 2 NumPy arrays, and I'm going to return the value. And I'm not going to return the actual value, but I'm going to return a reference to it, an object of future. So when I do read.array.remote, I'm getting a reference to it right away. Right? It's not going to read the file. It's going to start reading the file, but what you'll get is an object reference. And the same thing with file number 2. And now note, the difference over here is that I'm not sending the actual values of the file that's actually read. What I'm sending over here is the object reference that was actually returned by these 2 calls for me. And then I'm just sending the references over here. Now, when I send the object reference, what this particular Ray add is going to do is that, oh, I've got an object reference. It's not actually a value. So I'm going to dereferences. I'm going to go find out where this object reference is. And if you look at the object reference, we have an encoded value, how it's actually done. And it's going to get the value of those NumPy arrays after it's read from the file and return you. And then when I get the value back, the addition, note that I'm doing a ray.get. Right? Now, ray.get at this time is a blocking call because I don't know whether the value returned by this has already materialized, and I don't know the value returned by ID and ID1 above has already been materialized because it's the file that's actually reading. So this is sort of one of the blocking calls, right? But what happens over here is that these can be scheduled right away, and you get references back, and you just continue doing that. So that's one of the sort of fine bits about that. Yeah? It will start reading it, but you read it asynchronously, right? What happens over here, the read part of that is scheduled by the Raylet, and you'll just get a reference back, right? So this is, no, it doesn't wait. Yeah, you just get the reference right away, right? It'll be like within 1 millisecond, boom, you got the reference right. And then you can do a ray.get on it, and you'll see that it's blocking. But if it's ready, you'll be able to get the data.
So if I never call ray.get,
sir?
If I didn't call ray.get on it, it would eventually be computed.
Yeah.
It's not waiting for me to call
Yeah.
again.
I mean, ray.get is just saying that, is it materialized?
Okay.
If it is already materialized in the object store, boom, return me the value, right? So you're not obliged to call ray.get right away. You can call it later down the line as you're doing other stuff. But this is all happening in the background asynchronously. And that's the beauty of it, because you can create all these tasks and later on, get the values as they're needed. Something very similar with class actor is that you actually just say, for this particular array remote, I want a counter to have 1 GPU. and then you write those particular methods, and you create an instance of C, and then go ahead and increment any of the methods that you have. And the way you increment, the way you invoke its method is just use the function name, the instance, just like you do that in Python. You have an object, you create the method name, but over here we just have the suffix called remote. And then have any arguments do that. The same thing over here. In both cases, always return a reference, right? You always have to do array.get. And this is what we were talking about, is that when this actually happens, I have read.array that's actually reading a file and is going to return an ID reference right away. The other read array could be scheduled on another node, and it's going to return a reference. So there's this dynamic graph it's actually building. And then we're actually adding those two numbers and then returning the value of the particular reference. And then finally, we're doing array.get. Yeah.
So for the read array on file 1, you return the reference. You don't know how big that file is in advance, right? Is under the hood Ray's figuring out to distribute that over the memory on number of workers? Okay.
Yeah. There's a library called ray.data. You actually have, let's say, 10 gigabyte file sitting on S3. What it's going to do is it's going to read blocks of that and shard it across the array cluster, and then return you those particular blocks. And we'll see some of the particular example. I hope we have enough time. I'm going to run through the slides very quick. And then the object store that I talked about is this illustration of what an object store is. And it has a shared memory object store. And any of these worker processes on which the tasks are scheduled or the actors are scheduled, they can access any of the objects which have been created by that. And this is all zero copy. So I'm not doing inter-process copy. Now, it's not inconceivable that sometimes, your object store has a limited capacity, and you're putting a lot of NumPy arrays, you're putting a lot of images in there, and you'll run out of shared memory, and they'll spill to the disk, right? And you can specify what that particular disk is, whether you want it on S3 or whether you want an EBS storage or whatever high perform or NFS file system you actually have mounted on the cluster. That can be actually stored. And then when it's actually stored, it's actually noted in the GCS that this particular object reference that you have used to exist on node A, but now it's stored in the disk, and that's how you actually get that. And then this is some sort of simulation of how sort of shared memory actually works. Anybody actually has worked with shared memory? Okay, right. This was already a common way of how Unix shared data. You just create this /dev/share memory, provide that, and then you can just write stuff to it. And this is based on Apache Plasma, which is very efficient. And the calls to it are very simple. Do a get, do a put, do a wait, and you're done. Okay, and just to give you an illustration, this is actually what's happening. I have a radar.remote function that I have scheduled, so that might be executed on node 2. Then I'm doing another remote function, so that function is going to be executed or scheduled on that particular node, because Ray actually has an idea of data affinity. So if F is actually referencing a data that I know is actually stored over there, the Ray layer is smart enough to actually schedule it over there, so I don't have to do a copy across the node. And this is actually what happens over here. The G is going to schedule over here. Now it has access to both the data. So that's sort of what's happening behind the scene. Okay, so why would you actually use Ray? I'm going to sort of give you, and I just want to give you a quick high level before we actually get into the workshops. You can use Ray to build libraries. We actually use that to build our Ray runtime that I talked about in the slide. You can use Ray to build other distributed frameworks that you actually have. So for example, we have a version of XGBoost Ray, which you can actually do that. XGBoost today allows you to do distributed compute, but on a single node. Right? You can actually take 8 cores that you actually have, and you can distribute your objective function on that, or your algorithm on it, and it will distribute it across. But what about if you actually want it across the cluster? So we have wraparound that. Same thing with scikit-learn. Like Joblit allows you to do that locally, but now you can actually do it across. Ray actually also, you can write multiprocessors pool. We actually have multiprocessor pool that Ray. So these are all the Ray patterns that allows you to build those things. What are some of the other things that people actually use Ray for? You can use that for monitoring, experimenting. People actually have integrated Ray with that. And then finally, we have all these integrations. All these companies are actually using array to build their own platform, right? Because we provide you the abstraction, you can actually build additional, your own existing platform they actually have. We have integration with Hugging Face and PyTorch and AlPy and all those things. So that's what people are actually using Ray for. Now, it behooves me not to talk about Ray and not talk about large language models, because I think we have sort of entered this zeitgeist of this foundational shift. And luckily, Ray is just there at the right time. So what is the current state of the world with respect to foundational models? So you got these big tech companies, right? You got Cohere, you got OpenAI, you got Anthropic, you got Hugging Face, Stability AI. Every day there's new coming. These are sort of people who actually have deep resources. They have the deep engineering expertise. They have lots of money, and they can actually use the compute power to build foundational model from scratch, right? And fortunately, when we had our Ray Summit last year, Greg Brockman, who was one of the founders of Cohere, of OpenAI, revealed to us publicly that they were looking at some distributed frameworks to figure out how they can actually train GPT and how they can actually train ChatGPT, and then how they can actually use the reinforcement learning with human feedback. And they tried many frameworks and didn't work. The scaling just didn't work. And they decided to go with Ray because it gave them the primitives to actually do that. So those models were actually built using Ray. But what about if you and me want to use language models? What do? Right? We mere mortals actually have two choices or three choices. We can download some of the model from the Hugging Face, right? They have pre-trained weights, and then we can fine-tune that with our data. They actually want to do either summarization, or we want to do some Q&A instruction set for that. And then we can actually do serve and inference. But all these three things that we can actually do, mere mortals, actually has some challenges that we have to overcome. One thing is that scaling can be actually costly, because when you want to start fine-tuning these particular models, even if there are 6 billion parameters or 175 billion parameters, you need clusters to actually scale and distribute your training. So you can go with spot instances, but spot instances can disappear, right? And if they disappear, you can lose some of the state. So you have to have a framework that allows you to actually take control and fall back, or has the ability to recover from those things. And then most of the time, if you're actually using both hardware and CPU and GPU resources, sometimes you might have an ideal GPU just sitting there because your CPU is doing some computation and is waiting for a data to do this GPU inference. So you have to have a framework that can minimize the idle time, and you can do pipelining things. As soon as the data is available for one, it can be fed into GPU to do that. So you actually have to have the ability to do that. The other thing, that models don't exist in isolation, right? If you actually build a particular model, there'll be ensembles of model, right? You might have a model that's just doing a prediction, and they might take the prediction and feed it into one of the classifiers, and the classifier might give its data to that. Each of these separate models, which are built as a single unit of execution, might need different ways you can actually scale it, right? So these replicas that you actually might create, they have to have the ability to scale automatically. So you have to worry about those things, because there might be one model that's taking a lot of traffic and you won't be able to scale it and scale down. And then finally, when you're doing fine-tuning, there's a lot of tweaks that you will actually make. You want to do distributed training, and you also want to change some of the hyperparameter tuning so you can actually get the best pre-trained model and fine-tune that. So these are some of the challenges for mere models. And what Ray allows you to do, and one of the things that we actually done, is that we try to simplify the orchestration by making sure that the spot instances, when they fail over, we actually maintain the state and you can recover from it. The ability for you to actually do inference referencing and scale it independently. Ray Serve has the ability for you to scale independent replicas. And then training, training and tuning, Ray Train has all the wrappers around PyTorch and TensorFlow and XGBoost to be able to do that. So if you're writing all this boilerplate to do DTP with PyTorch, you don't have to do that. You just use the Ray PyTorch trainer, and underneath it will actually do all the boilerplate for that. So the way we actually use PyTorch is that if you're doing distributed data parallel, We create the process groups, and then underneath, the Python processes do the gradient synchronization. So all that code, you don't have to worry about it. That's done for you. And we begin to see two emerging stacks in the open source community today. You've got people who actually want to build foundational models from the scratch. They can use JAX for it. They can use ALPA that allows you to do model parallelism, because if you're building 300 billion parameters, you actually need to be able to build models in parallel or do the inference at the same time. And they're using Ray for the orchestration for both GPU and CPU. And then they can actually compile some of the ALPA code that you actually have, and then you can actually run that on a GPU accelerator. So these are the people who actually want to build open source from scratch. These are all open source stack. You can actually use that. The thing you have to pay for is obviously this thing over here, because that can be costly. The other stack we actually see, you already have a pre-trained model, and all you want to do is just a little bit of tuning, a little bit of training. So you download the Hugging Face model. You can use the deep speed accelerator that we actually have integrated with that, and you can use the PyTorch framework, and then use Ray for acceleration. And then you can use any GPU that you actually want, that your hardware, that your GPU supports, right? So this is building from scratch. This is taking an existing stack that you have, and then using all open source that you actually have. So that's essentially what we talk about. And what we have done to verify that, to give you a social proof, to give you guidance, we have created a half a dozen blogs that actually tell you how you can actually use Ray for all these things. So if you go to any scale Go, you have a series of this particular blog that give you the notebook that actually gives you exactly how to do it. And this is a validation for us to say, open source is here, right? You could actually work with the proprietary stuff, but this is also good that you can actually use. And these are the companies who are actually using Ray. And we actually have a specific talk that you actually want to attend on Friday, which will go more detail into how LLM is actually used. And we're going to train a FLAN T5 model to see how you can actually do that. Okay, so takeaways. Distributed compute is a necessity. Why? Because ML is very pervasive. Our vision is to make sure that it's actually easy for anybody to actually use it. And Ray libraries allow you to scale your machine learning workloads, and Ray offers a compute substrata for generic workloads. Okay, we have a summit coming up. Anybody attended Ray Summit before? Okay, we have a Ray Summit coming up on September in San Francisco. Good reason to get out of Northwest and come down to sunny California. September the 15th through 18th, I believe, when we have a full day of training. So guys from Denmark, you guys can come over. Okay, let's go to the code now. Any questions before I get into the workshop? Yeah.
I have a question. Are there any libraries and integration for deployment? So like particularly on Kubernetes,
Yeah, so when you're running Ray on Kubernetes, there is a kuberay operator that allows you to do that. Oh. Right. So there's a kuberay operator that can scale your pods actually one. So if you're running on Kubernetes with Ray, you use the kuberay operator to do the orchestration. And if you're using Ray Serve to scale the replicas, there's a Ray Serve operator that does that. So yeah, we work with kuberay very easily. That's why I say you can actually run on Kubernetes with the kuberay operator. And that was a community contribution from Microsoft and I believe Google and Anyscale. Yes?
There are some workflows that I can figure out how to run this part person that is interested in this way to accelerate things.
I can't hear you.
So there are some workflows that I can implement in Spark.
Yeah. Mm-hmm. Do you
know what the performance?
Yeah, good question. I think there's certain workloads which are very good for Spark, right? So if I was doing, say, ETL and EDA, I wouldn't use Ray because Ray is not equipped for that. If there are certain batch inferences you're doing for at massive scale, then Ray excels that. We actually have some performance numbers which are going to come out next week. We've written particular blogs. You actually see how we have compared both Ray, Apache Spark, Ray, and SageMaker to do batch inference at scale, and then give you the performance number. The other workloads like data transformation and all that actually does vary, right? So if you're using pandas, if you're using PyPandas, you can use particular Spark. But today you have Modern, which is distributed pandas, so you can actually use modern Ray, right? So there are all these differences you actually think about that. And the other problem is that you now actually have two different clusters. You got a Spark cluster and you got a Ray cluster, right? I look at it this way, and this is, I'm a big fan of Spark because I worked there for 7 years and wrote a book on Spark. I look at it this way, is that they're very complementary. The Spark does good things for certain things, and I believe that the journey of a machine learning data scientist ends where the journey of the data engineer ends. So once your ETL is done, once your data is cleansed, everything is ready. In the case of XGBoost, structured data sitting on the table in S3 or in Delta Lake, you can now hand it off to the Ray to be able to do that training, because now you already have the training. You might use last mile transformations, right? Where you might want to change the image, or you might want to do some scaling of the image. Those can be done with Ray data that allows you, has the preprocessors that run with the training loop. So yes, there are all those things. I don't have the numbers, but next week we might have numbers with one particular workload. Right.
Do you have a sense for the XGBoost?
I don't have one for the XGBoost. Can you talk to me? I might have something in documentation that we actually did some numbers, but it's no comparison. We just saw some numbers on Ray where they're more about how XGBoost on one core, how is it on 6 core, how is it across distributed. But now we haven't done those comparisons. Because one of the things that when you run distributed training on Apache Spark, you have to use Horowod on top of that, right? Because you have to use Horowod to do the distributed training. And that allows, that's an additional layer that you actually you have to take into account. Any other question? Okay, how many of you are successful to put Ray, see, this is what happens when you work for a company for too long and you can't get the things out of your head. How many of you put Ray on your laptop? Okay, this is optional. I mean, I just wanted people to somehow, you can follow along by just going to the particular notebook that you actually have. So these actually have 3 modules. We're not going to cover all of them. I'll try to cover at least the first 3 if I have the time. We have about 45 minutes. So let's go into the first notebook. You can see the screen? Okay, so you've seen this particular slide. All I'm actually doing is showing you how you can take an existing Ray application that you actually have, which is serially in Python, and then convert that into a parallel execution. And the task of parallelism pattern is very simple. You can actually either have one worker that's executing all these particular tasks, or you can actually have Ray schedule all these tasks on different workers, and now you're actually executing in parallel. So this is the parallel execution versus serial execution, and we'll get some of the examples of that. And the way you actually do that is if you actually have a function, once you actually put the Ray decorator on that, you can actually use the function named remote to be able to just send arguments to that to execute remotely. So we're going to do something very simple, generate the lazy Fibonacci series. So I have about 10 million or 100,000 numbers that I want to create in the Fibonacci series. And I'm just going to create this particular generic Python function that is going to take my Fibonacci number and then calculate those Fibonacci series and then return me the length. I don't want to return all the numbers because it's just going to be too big, but I'm just going to return the length, which is going to be 100,000. And then I have a remote function, which all I'm doing is I'm just decorating that particular function so that I want to now run it remotely. So we're going to do that. And I want to find out how many CPUs do I have so I can create that many tasks separately. So I have 10 of those, right? So that gives me train. And then I'm going to have another function that says run this locally, right? And then this particular code, I'm just using comprehension to go ahead and create 10 tasks serially. Each of these is going to compute, Fibonacci series for 10,000. This is just an illustration to see how long it actually takes running sequentially in parallel. So let's run this in local mode and then time it, and you'll actually see that it took about 1.9 seconds to do 10 tasks to compute all the Fibonacci series for that. So now let's actually do that for array cluster. Did I actually start the cluster? I normally, whenever I'm doing more notebooks, I go in and sort of restart the cluster on my laptop, so I start everything from scratch. And there is a dashboard that actually comes with that, and we'll get into that in a minute. That actually shows you the metrics and all that. All right, so we did that serially. Now what about we actually do that run remote in a distributed manner? And so when you do a run remote, what am I doing over here? So run remote is doing exactly the same thing, but the only difference over here is that I'm executing 10 different tasks remotely. And each of them will get 10,000 numbers, and it will execute in parallel, and then I'll get my results back as the object reference. So that's what actually is happening over here. So we're going to run that, you can say 25 milliseconds, right? Now the difference between the wall time over here and the wall time over there, you say, well, why there is a difference between those two? This particular wall time takes into account that, remember, you're actually doing array.get, which is a blocking call, right? And that's where the additional time is. But you can say there's a significant difference in something executing serially and something executing using array. Now, for exercises, normally when I have this all-day workshop, we break at this point and you guys start doing the exercises. But I have solutions over there, so you can actually look at that tonight if you actually want. Let's do something else. Let's do something interesting. Let's see if we can actually compute the value of pi using the same mechanism, using serially and then using in parallel. And the way we actually compute using Monte Carlo simulations is that we try to get as many spots or many data points between this one by one square and the concentric circle. If they're inside, then we can actually do that. And we take a ratio of that and then compute what the pi is. And so we're going to take, again, 10 tasks because I have 10 CPUs. If you have 20 CPUs, you can actually do 20 CPUs. I'm going to calculate about 10 million data points. I want to, as many data points as I have, I'll probably have a better approximation of pi. And then so my total number of samples is going to be my total number of tasks I'm going to run times the number of data points. And then I'm going to use this particular function to determine if the random data point between -1 and 1 falls into that particular circle. And if it does, then I just compute that. And if it doesn't, then I go home, right? So let's do that run serially. And again, serially, I'm doing the same thing. We're actually using a comprehension list to go ahead and create 10 tasks serially. And each task, I'll just assign a task ID so I know this is task 1, task 2. And then we're sending the same sample size up to the serial. And we're going to go ahead and do that. And likewise, for distributed, we are just going to put array decorator on top of that and then return an object. And an object over here is whatever is returned by the sampling function. And the run distributed does a couple of things here, right? First it actually does the same thing as the serial one in the comprehension list, and then I'm just putting array.get around it. Now notice that I'm actually doing array.get after all of them have been executed. If I put array.get inside, what do you think will happen? It will block on each and every call, right? So you'll just wait for it to finish. Whereas over here, I'm saying go ahead and schedule all those things, and when you're done with it, when I get back my object reference, because what this will happen is that it will go ahead and schedule all these 10 tasks remotely and return me the object reference right away. And then I'll just do array.get. And when I do array.get, I'll get the sample of that. And I just took the sum of all those and I'll find out. So the way we calculate the pi is take a ratio of those things. And now let's run this serially. So when we run this serially, you can see that the task ID, so the first sample task ID took about, 7 million of those. So these are all the data points that fell into that particular inscribed circle within the square. And this is all actually happening serially, and you'll see a difference between the parallelism of that. And then we actually estimate pi. Okay, so we got the value of phi up to phi significant. Not bad. Now let's try to run this in a distributed manner, right? Same thing. We're going to run this in a distributed manner, and you can actually see now that there are 10 different tasks. Each of these is a different process. Now, because I'm running this on my laptop, I have 10 processes running, and each has a PID ID. But if I had clusters, then this would actually be running on a particular cluster, right? So I have 10 tasks, although you can see they are sort of all running asynchronously. They've been scheduled. And then it took about, 42 milliseconds compared to what it took me for the serial one. So you can see the difference between, running something serially and running in parallel in a very simple manner, right? All you had to do was just decorate your classes or your functions, and you would actually do that. So just to recap, you can actually use these array decorators to be able to take any of your functions that you have and then convert that into a distributed setting. Okay, now let's do another example where this is something that you actually might do, which is very common in doing deep learning, where you actually have all these images that you are going to transform them before you actually give it to training. You might scale the image, you might do some segmentation, you might do some masking, you might resize the image, you might flip it. So what I'm trying to show over here is that you can actually do all these transformations on the image that you have, and you can use Ray to just distribute those transformations, and when you get the transformations, now you can actually do training with that. And you can do that very easily with the Ray task. So what I have, we have some import utils that I have, and I'm going to take all these images that I have, which are large images, and I'm going to create them into batches. But for brevity, I've just scaled down the batches to be 28, 40, 60, and 80. And for the time, I'm not going to run those things. I already ran it. So what I'm going to show you over here is walk through the code that this particular array function, all it does is transforms the image. And the transformation does a couple of things. It does some random matrix multiplication. It flips the particular image. It scales it to a particular size, and then it does some other torch multiplication. This would be something that you would actually do for your images. Then you can actually do that in parallel, and then returns the value, and then we'll try to see what those images look like after they've been transformed. So if I run this serially, this is my code that just downloads the stuff, and I'm going to look at the image, and that's what the images actually look like. Random display, and I'm going to go ahead. God, I hate this. So if I run this serially, you can actually see that the first batch took about 13 seconds, the second one 28, the third one was 48, and the last one was 60. And if I ran that in a distributed manner, the only thing I did between the serial and distributed was I took the images and I put them in the object store, right? I put the images and I put them in the object store, and then I can just get those images from the object store, right? And that's where the object store comes into play. So this particular object store now actually, this is one node, so I actually have one object store, and then I have all these workers running will actually fetch that particular value. So this is what I'm doing. I'm taking all these images and I'm putting it in an object store. And notice that what's actually returned is just a list, right? I've just returned the particular list of the object references. And this is sort of an encoded data that tells me where the object store are, what machine it's running on. You don't have to worry about that. This is this 32-byte encoded string that's meant for internally reference. And when I run that in a distributed manner, you can actually see the time difference between 5 seconds, 9 seconds, 11 seconds. And then I do a plot. And you can see when I do a plot, you can actually see the huge difference between how we actually took to do that. And all those transformations were done in parallel. Any questions? You have all that code, you can actually run it. Okay, we got half an hour. Okay, let's go to the second one.
Can you auto-scale like the number of nodes you need with Ray?
So Ray comes with this built-in autoscaler, right? And what happens is that let's say you have 5 nodes, and you have 20 tasks. Who asked the question?
I did.
Yeah, and you have 20 tasks you actually do. Now all the tasks have been filled in, and now you're actually scheduling more tasks. What the autoscaler will do is it will actually start a particular node, 2 or 3 nodes, based on your need, and it will register those with the GCS, and then GCS will broadcast that to the Raylet, and now you actually have 2 node edit, and the queue that was pending now is actually scheduled. So yes, you can actually do auto-scaling. That comes with the open source version of Ray. So yeah, there is an auto-scaling. Over here, we don't auto-scale because you're running on your laptop. But if you're running on, let's say, AWS, when you actually create your cluster.yml, you can actually say how frequent I want the auto-scaling. So do I actually want to wait for 1 minute or 2 minutes before I say go ahead and do that? And you can do it up to, and how many? So, yeah, you can say maximum number. Obviously, there's a physical limit of how much money you're going to pay. But in certain cases, yes, you might create a 10-node cluster and you want 5 extra nodes to be added, which should be the same images that you actually create in your cluster.yml. So whether it's a Docker image for your EC2 instance, or it's on Azure or even on GCP. Yeah, so auto-scaling is part and parcel of the open source.
Is it a function of the underlying infrastructure as code, or is it specific to, like, for example, public cloud, or how do you implement that?
Well, so if you're running on, say, AWS, and when you do an auto-scale, we already have the image of that you actually created, and we just use that particular image to
Ray is doing that, or
Ray, the auto-scaler Ray is telling the AWS cloud provider, go ahead and create those instances. So the autoscaler is the one that's actually written in Ray. The underlying launching and the provision is actually depend on a cloud provider, right? So using the REST APIs, they go ahead and create this particular image, right? Because it knows already what your images are.
So no, actually, sorry. So is it spinning up a node, or is it spinning up a node via Kubernetes, for example? And
if you're running on Kubernetes CP, yes, it will do that. If you're running on AWS, it's going to spin up an EC2 instance with the same number of nodes that you actually have, right? So let's say this has 8 workers, and I have autoscaler. You'll actually create a replica of that, right? Whether it's homogeneous or heterogeneous. I mean, you can't change the configuration on the slide, but it's going to be the same thing. Okay, so this particular exercise, all it actually shows is how you can actually use memory object store to be able to take advantage of this in your tasks and your actors. And so we already talked about it, and all I'm going to show you over here is what am I doing in terms of doing the same thing. I have some massive NumPy array, and I want to transform those before I actually do anything with that. So we actually use the object store to be able to actually do that, and that helps quite a bit. Okay, so let's go through the code over here. I know this is a lot of code, but when you actually have the hands-on exercise, you actually get the feel of what it is. So bear with me. So my remote object store, I'm actually creating these particular random tensors that all it does is just create tensors of random value and then returns those random value. And then transform is a remote routine that actually takes that and then creates that. And the transform can do any one of these things. So I do all this massive transformation actually happening in parallel. So we create a transform, we put it in the object store, and then we finally return the list as comprehension objects. So these are the lists. These actually now, when we do array.put with all these different tensors or different tensor sizes, I get an object reference right here. And this is the object reference that I'm going to send it to my actor or to my task to do that. And then when I send those object reference, wherever task it's actually scheduled, it'll try to do array.get on it because it'll implicitly say, okay, you send me a reference, I'm going to dereference it, and I'll get the value, and I'll work with that. So you can see what's actually been returned over here is a list of object references. So if I just give you an idea of what it means, so I just take the first value of object, I do a val reference on it, I do a get of it, and then I get the value of the tensor. You can look at this, what the value of tensor looks like. So that's what I mean by doing array get and array put. Okay. So let's transform the object store in that. So here, in my comprehension list, I've taken the entire list. I'm taking one object reference at a time. I'm sending it this particular function, and once it's transformed, it's actually returned me a transform version of the object reference, and this is the new object reference. And one thing to note that these object references are immutable, right? So once you do a put on that particular object store, you can't change it. You have to create something else. They're immutable, so you can't change that in place. You have to create a new one to do that. And when I get the values back, you can actually, these transforms have actually been already transformed. And all that happened actually in parallel using array.get and array.put. Any questions over here about object references? Simple concept, a lot of things actually happen behind the scenes that you don't have to worry about. Okay, one thing to note about object references is you can actually pass them by value, or you can pass them by reference. And depending on your scenario, when you want to use one or the other. Okay, so here we're going to create a very simple function called, given a particular argument, just echo, tell me what it is, right? And I'm going to create some values over here. So we'll just go ahead and... So first I do pass by value. When I pass by value, I'm just sending in the actual value. And since this is echo.remote, it always returns you some object reference. Now, we're not returning a value, it's just a null value, but the function will always return an object reference. So now we're going to go ahead and send an object reference and see what actually happens over here. So let's do this. What happened to my thingy? Let me just run all this to the end so we actually have an idea. So object reference is actually great because you can actually, things pass by value and pass by reference. And over here, I'm actually creating this particular list and I'm passing by value. So when I do that, why is it not running? So you can see the argument returned was just 25. Even though I sent the value by value, it's just going to return 25. On the other hand, if I just send the object reference, it's going to do the same thing. It's going to dereference that and then print the value, right? If I pass by reference, and why would you want to actually pass by reference? It's possible that you actually don't need the value right away. You need some value down the stream that you're actually passing on. So if you want to pass something by reference, what you do is you put that into a dictionary, you put that in a list. So the receiving function would know that, okay, this is by reference, I'm not going to dereference it. By default, it's going to dereference it. So if I send this particular value over here, you can actually see that it did not dereference it. It just printed out the value of the reference itself. And I could just keep on passing the reference down the stream elsewhere where the value is actually needed, then I can actually do a array.get. So this is sort of a good way to manage those. And if I do the echo of this again, same thing happened. Now, I think the question is, well, what happens if you have long-running tasks, right? How long do you actually do array.get? How long do you actually wait for it? You have to have some sort of an idea that I'm going to time out at certain times, because if you have large functions that block for any particular reason, right, you want to start debugging that thing, what happens then? So I have a long-running task, and I'm just going to go ahead and create this function and return the answer to the universe. And I'm going to time this function. And what I'm doing over here is this. I'm going to do array.get, but I'm going to put a timeout on it, right? And the timeout is going to be 6 seconds, and I'm sleeping for 10. So obviously I'm got an exception at one point, right? So let's do this. If I run this, it's going to block for about 6 seconds, and then I'm got an exception because I timed out. So this is sort of good way to say if your array.get is taking too long, you can actually put a call around it. There are other ways which are more programmatic way to do those things. Let's say you actually have a large list of object references, and each of those lists might take different time. What you can do is you can do array.wait on that particular list and tell you return me the numbers that have actually already been finished. So what you can do is you can actually put in the while loops and saying, go ahead and iterate over this, and then just return me the ones that actually have finished. So what you get is the two lists. Ones that have actually finished and ones that are still pending, and you just iterate over that. Right? So that's sort of one way to say, if you have a large object reference list and each of them have different times to materialize, you can actually use this particular array.get to do that. Any questions? Yeah.
Seems like once you have your remote attribute on a function, that you can no longer just call it as a regular function?
No, but once you put that remote, we actually serialize it and send it to the remote node to actually do that. Now you can't call it, you'll actually get a syntax error. Yeah. Yeah.
So you had said that when you do a put, it's immutable. What if you put a mutable Python object into one of those values? If I put in a list, can I call append on it later?
Well, if you do a put, then that Python list is going to be immutable. What you can do is you can do a get, you get a copy of that, make a copy of it, do your transformation, then you put again. Because array objects are immutable. That's the whole reason what you want. Otherwise, you're going to run it all, because they can be passed over. And how do you actually maintain the mutation across different clusters that you're passing? So the way people actually change mutations is they will get a copy of that particular, for example, I put all my images in there, I did the transformations over there. And then once I'm done with those transformations, I do a reput again. And then now I actually have a new list, because every time you put, you're actually going to get a new reference to it. Right? The old reference is not going to be changed. This is something very similar to RDDs, when you have those sort of immutable objects, and when you make a transformation, the original object is not changed. Right? Every time you do an action, it will do that. And this is one reason why you can actually recreate those things. So this is actually good for us to do failover. So let's say you're actually doing something and something actually fails over, so we can actually recreate all the objects that you actually put in the store to the state where it was before. If you start changing those things, then we don't actually have that.
Does Ray use reference counting or some other method so that once one of those objects is in the store is
Yes.
needed, it's removed?
Good question. The question is, does Ray actually use? We actually have a distributed reference counting that keeps track of which objects have been created by who and how long, how many pointers are pointing to that. And when that comes down to 0, which is a very similar technique, we remove those objects. The primary copy will remain over there till the Ray task is finished, and then if there's no references, we just delete the primary copy. So there's a difference in primary copy and secondary copy. The primary copy is the one that the original creator of the function actually created that. So if it's a driver that created that, or a particular node that actually created that owns the primary copy. And subsequently, everything is actually secondary copy.
Primary copy lives on a single node, and the secondary copy is like if you have
On
A on one node.
Right. Secondary copy is on demand.
Okay.
Right. So if there's a primary copy sitting on node A, and there's a function that was to which you actually sent the reference, it's somehow scheduled on node B, and it needs that. It's going to dereference it and say, I don't even my Raylet tell me where it is, and Raylet will actually copy that. So those the two threads that I have, Raylet and object store thread, those are responsible for doing all that. And that's sort of the beauty of that. You actually don't have to think too much about that. You just do Ray get and Ray put and do that. Obviously, you have to worry about how big are the references, so you can do Ray.wait and all that. So these are sort of primitive functions, right? That sort of give you the power to do that. Now, as you take other classes that we actually teach, where you don't have to worry about doing Ray get and Ray put. All of our runtime libraries just take care of that for you. Okay, I'm going to skip that for brevity. I wanted to introduce you to Ray actors. So as I said earlier, the way Ray actors work is that when you actually create an instance of a Ray actor, the Ray actor takes over the entire worker node. It's sort of scheduled on that particular work, and it's dedicated to it. So let's say you have eight cores, and you have 8 workers running, and I create an instance of a Ray actor, and somehow it gets scheduled on node A. It's going to take over that particular worker, and now that worker becomes an actor, right? And any calls, any method instances that your reference actually has are going to be scheduled on that. They'll be sent to that particular Ray actor. It's conceivable that you have other actors running on the same code, on the same node, but they'll be running on a different process. So that's how it actually works. And the way it actually works is the Raylet says, okay, I have this particular actor, and it needs 4 CPUs. I don't have it. Who has it? It's going to send a broadcast. We call broadcasting list. And once it actually gets a list, it will know that, okay, I'm just going to schedule this over here and then let that particular Raylet take care of it. And any calls after that will just be scheduled on that. So that's how it actually sort of, at a high level, the scheduling actually works for Ray actor. And then once you actually have the Ray actor, now, whatever the driver code that you have or whatever Python application that they have, when they actually invoke that, we just make a gRPC call and send the data, and it will get executed on that. All the methods that are on that particular actor, if you invoke them in a particular manner, they'll be executed in a serial manner. There are ways you can do async. So if you define a method async, the actor becomes now asynchronously. So if you didn't want to serialize the invocation method, you just wanted them to execute asynchronously, you can do that asynchronously. And we implement async loop underneath the actor that does that. Okay. Okay, I ran this already, so I'm not going to run through this because I think we only have like 10 minutes left. So what's the first problem that we actually might want to do with Ray actors? This is a good use case. Let's say you're doing telemetry, right? You want to find out you create a particular package and you want to find out who's actually using that particular package. This is a very common problem that we actually use when you want to do telemetry. When you release a new open source code and you want to find out, how people are using it, what libraries are actually using, this is sort of a good way to find out what methods are being actually used for my particular actor. So in this particular use case, I'm creating a couple of actors that I actually have, and I'm invoking those particular methods. And based on that method, they'll be sent to either actor 1 or actor 2. And I keep a counter of who actually invoked me and how many times they were invoked. So this is sort of a diagram of what this particular array code is executing on the driver or on my Python script. And then these are the actors that is talking to, and I'm keeping state. Remember, actors are the way that you can actually keep state of it, and that's the important bit. So I'm just creating a class over here, base class that actually has some constructor arguments, a method, a dictionary that I keep track of, the method name that I actually use, and I keep a count of it. And then my method could be any generic method I'm doing, and I'm sending in some key value arguments, and I might do something with the key value arguments, right? And then some method functions will get those particular method and then get the name. So those are sort of base class. And then I'm going to inherit this class, and I'll decorate that with the array.remote, and I'll implement my do something method. Now, the do something method could be something easy, or something relevant to you. Have the command line arguments that you might want to put in the database, or you might write to a particular file, or you might do something with it. So that's your array.method that we have. And then after that, you want to update that particular counter. So that this method was actually called with this particular arguments. So you kind of have a way of collecting telemetry data. And same thing with the second class. I actually do the same thing over here. And I'm going to create 2 instances of that. I create the instance 1. I call it my actor 1, and second instance actor 2. And in this particular logic over here, I just have some variables that says I have a list of actor 1 and actor 2. I assign them with the instances of those. And I'm just going to have a little for loop that I randomly choose between those 2 actors, and I call those, in a list. And I'm saying, well, if my method is 1, then I'm just going to go ahead and store my values in the store database. If it's actor 2, then I'm going to call and put it somewhere else in a key value store and return it. And when I do that, I get my counts. And then finally, I can do this array.get to see what was the end result of those calls. Very easy, simple case. But you can see that actually maintaining state, right? And you can maintain state for a lot of things. And array actors are very primarily used in our array libraries, because if you look at how train works and how array tune works, all these actually create actors. And these actors are sort of managing state of a hyperparameter tuning of your results. So if you're doing a fine tuning, you actually find out what your metric values are. So all those are created and they talk to each other. And so that is a crucial part of our array air libraries to do that. And I can actually look at my dashboard to see what these look like. Now, one of the things about the reason you can't see the metrics over here, because in the open source version, you have to install Grafana and Prometheus to be able for us to actually put all those metrics. But if you're using the managed version of Anyscale, you get all that particular free. So it's not that you don't get it. All you do, if I install Grafana and Prometheus over here and then tell the array to say, this is my local version of that, go ahead and put the metrics, and you'll be able to actually see all the metrics. And these are all my actors that ran. Some of them are dead already. So that was an example of how we actually use array actor. The other thing I wanted to show is that how you can actually use the same thing that we actually use in our first example, but we're going to use array actor. And the way you're going to use array actor is that we're going to use array actor that keeps progress of the Pi as it's been computing by the tasks. So in one way, we actually did a stateful way where every task was actually created and just returned a point. Over here, we're going to have the same thing, but we're going to have Ray actor that keeps track of how far we actually have gone in maintaining the Ray actor. So I'm going to create a class over here called progress bar, and all it's actually doing is keeping track of all the task IDs that I have, along with the number of samples that I actually have completed for me to be able to create a progress report. And I have some function calls that says, go ahead and get the progress of that. And the way I compute the progress is the total number of tasks and how many have been computed, so I get some sort of percentage. And then we define our task, which was no different from our previous version in Ray tasks, but I'm just make that as a remote task. I define all the different variables that I actually have, which is pretty much the same thing. And I want to have the frequency at every 1/1,000,000th of the data point tell me, give me the percentage of where we are. So that's sort of maintaining the state. I go ahead and create this particular actor instance. And then using this particular comprehension list, I go ahead and raising this, this in the loop, I just go ahead and create the task, and I call my prosing actor, and I just do a get on this, and you can actually see it's actually returned me the progress as we actually go along. Right? And the way it's actually doing is that this particular here, progress.remote, is the one that's keeping the state of that. And the Ray tasks are the one which are actually getting a value or a reference to the progress actor. And remember, I'm sending in the handle to the actor over here. So the Ray task can actually update where I am. So if you look at the Ray tasks over here, Ray tasks gets a handle to the actor. And now it's actually, once it's actually done the computation, it's going to send a message to the Ray actor using this particular call. Progress actor.report the progress for that particular task ID, right? So these tasks are executing in a parallel manner, but they have a reference to one actor that's keeping progress of that. Simple idea, but these are the things you can actually do. And then we just compute that. So what we actually shown over here, there are two ways you can use actors. Actors are stateful entities that you can actually keep track of that. You can schedule them on any particular Ray cluster. You can assign them resources that you actually want. I want to use one CPU, I only want to use GPU. You can send actors as arguments to other actors. You can send actors as arguments to the tasks, and the task can send messages to that, right? And you can have multiple actors running. And I think in the next one, we'll actually show that. I have 3 minutes. I can't go over, can I? I can't hold these people captive. Half of them are going to sleep. Okay. I wish we had more time because there's so much good stuff over here I wanted to share with you guys. So this is a very design pattern that's very popular in our Ray libraries, which is called a tree of actors. And actors is fundamental to some of the Ray implementation across all the libraries, whether you're using tune, train, reinforcement learning, or Ray-So. And the idea over here is that I have a driver or my Python script that's going to create a number of supervisor actors, and each supervisor actually has a bunch of actors that actually creates, and these actors now communicate with the other keeping state. And then finally, the supervisor can actually query the actor, where am I? And this is no different. Let's say you're doing hyperparameter tuning, right? You actually create a trainer, and trainer actually has a tuner. It creates all this particular task. Each task has to report after a particular trial, what was the loss, what was my learning rate, all that metric. And those can be actually kept state in each of these individual actors and can be back and can be reported. So this is a very common design pattern used exclusively and entirely in all of the libraries, and you can use that as well. Hyperparameter tune uses that, Ray tune uses that. And the idea is for this particular example, we are doing same data, different functions. So what I'm doing is I have 3 different actors that will train XGBoost, that will train linear regression and decision tree and with the same data, and then give you the results of what was the best particular library that was used. Can I do that in 1 minute?
Yeah.
Can I do it in 1 minute? Okay, good. I ran it before. All right, so I did. So this is I'm training this data on our California, not Seattle housing database. So I have this particular data. I'm going to create a generic class factory that allows me to use 3 different algorithms: random forest, linear regression, and decision tree. Okay. I'm going to create an instance of a supervisor. My supervisor actually creates 3 different actors, and now what I have is, and then I'm just going to get the results of this and then find out the results of how they actually did. So I create a supervisor. I launch each and every actor. Each and every actor now is running independently. One is doing XGBoost training, one is doing linear regression, the other one is doing decision tree, right? They're using the same data, California housing state, but they're running in parallel and they're keeping state and they're communicating with the supervisor. So here we actually see these are 3 of those running. So I've got XGBoost that ran. I have decision tree somewhere down the road. Yeah, I have random forest and I have a decision tree actor. All of these are running in parallel. And I just have a loop that sort of keeps state of where it is. When I'm done with all of those things, I get out the loop and I get the sorted value of all the results. So what the results are being returned by each and every algorithm is the MSE. And I want to get the best MSE that I actually have. And so I run them, and you can see that the results are, I've used 150 estimators. These are the hyperparameter initial tunes that I actually used. And I get the MSEs for all of them. And if you look at the dashboard, you actually see all those running in parallel. Damn, I did it in 1 minute. This would have taken longer, though. But the fun part is that you guys get to do it. I don't have to do it, right? But, unfortunately, I don't have enough time. But thank you for coming. And you have this with you.